Hey learners, Jared here, and welcome to the video walkthrough for the hanging mass free response question that was in all of the versions of our forces test. So we'll be going through the free response questions and then also how the points were allotted for that free response. So in this question, we have a key phrase that a lot of people missed, and that was that this system was moving at a constant speed. Constant speeds, that means that we are at kinetic equilibrium. So all of our forces need to add up to zero. Our acceleration is zero while this system was moving. So forces that we had on our block, we had tension from the string. We've got normal force coming off of the track. We've got the weight dropping straight down. And then we've got, as it slides up the ramp, it's got kinetic friction, back in the opposite direction it's moving. And that kinetic friction isn't equal to the tension. There's components there to our weight vector that we'll look at in just a second. But those are the forces that we would have on our block. And those of you that drew the components to your weight vector, you can't do that when you're drawing a free body diagram. It's just the forces. It's not the components to those forces. And then forces that are on the hanging mass. You've got the tension, and then you've got the weight of that hanging mass, and those two will be equal to each other because, again, we are in equilibrium. So that's MH, MH for hanging mass G. And the point breakdown for that, if you had, for your block, if you had tension and friction, that got you a point. And then if you had normal force coming off perpendicular to the surface, that got you a point. And then if you had the weight coming straight down, that got you a point. The last point for this problem comes from getting both forces on the hanging mass. You didn't have to draw them equal to each other, but you did have to draw both of them to get that fourth point. Okay, so the next part is where we are coming up with the expression. Derive means to go through and show every step to solve for that hanging mass. And we can express our answer in terms of MB, theta, mu k, and then any other physical constants, meaning we can use G in our answer. And to do this, this is basically what we've been doing for the, a good chunk of our review. It was an Atwood's machine, but it was even simpler because there wasn't any acceleration on our system. Everything was balanced already. There was no net force on our system. So when we go to sum all of our forces, so here, let me erase this real quick. When we go to sum our forces for our system, it's going to be 0. And when we look at the forces acting on our system here, I've got normal force coming off like that. I've got weight coming down like this. And then we've got the kinetic friction coming back like that. And drawing it like this and getting all those forces in a line And I'm also going to draw my y component to my weight, and then my x component to my weight. So when you draw it like this, remember you can kind of eliminate tension along that string. And we've got the weight of the hanging mass, which would be mhg. That's the force that's pulling this block, MB, up the ramp. So mhg, I'm going to take this way to be positive and then this way to be negative. So mhg is the only force I have pulling up the ramp. So minus all of the forces that are pulling down the ramp. So FGX for that block and the force due to friction. Now, where the mistakes were made is that, okay, you set that equal to the mass of the system times the acceleration of the system, and then everyone had this acceleration term left over in their answer, and they didn't know what to do with that. But that's because this whole side is 0. So solving for mh, we just need to add these terms over to the other side. So mhg is equal to fgx for our block, so right here, and then fk, the kinetic friction. And when we're solving for those, fgx is the opposite to our angle right there, our angle theta. So it's the opposite, we'll use sine. So, oops, fgx is going to be mbg, the weight of that block, times sine of theta, plus the kinetic friction, which would be mu k times Fn of block B, and Fn is going to be equal to Fgy, that y component. So this would be plus mu k times Fgy, which is mbg cosine of theta. And on both sides, I've got g. And you can kind of simplify it a little bit more by factoring out that mb, but you end up with the hanging mass being equal to this right here. So mb times, I'll go ahead and factor it out so it looks a little neater, sine of theta plus mu k times cosine theta. And the point breakdown for that is if you knew to start with, if you knew to start with the summation of your forces equals mass times acceleration. So if you knew I got to start with Newton's second law, that got you a point. The next points I made if you set that equal to 0. And then I only made it worth 1 point if you actually got to the right answer. So if you knew just the gist of how to start this problem, I gave you the majority of the credit for that problem. But that's our hanging mass right there. Okay, so it's determined that MB is 2 kilograms, the angle is 30 degrees, mu K is 0.1, and while the block is moving up the ramp, so the block is actually still sliding up the ramp, the string is suddenly cut. And part I is to determine what is that acceleration of the block after the string is cut. So again, we're doing acceleration, which means we've got to sum our forces, mass times acceleration, and we're doing this for the block. But here's the thing, that block no longer has any tension, which means these two kind of components, FGX and FK, are both working to stop that block. Now, you can make your life a little bit easier by saying, okay, well, down the ramp is positive. And then you would end up with FGX and FK working together to cause this acceleration down the ramp. If you make down the ramp negative, then that's okay. They're both going to be negative. But it doesn't matter because it says calculate the magnitude of the acceleration. The key was having these two forces work together to slow down the block. And so solving for that acceleration, we would have the mass of the block times g times sine of theta plus mu k, mass of block g cosine theta, equal to the mass of the block times the acceleration. And we can cancel out the mass of the block. And so we're left with acceleration is this. You plug in all of your values, and you should have gotten an acceleration equal to 5.87 meters per second squared if you plug in all of these values. The key to that was having those two forces, FGX and FK, work together. Some people just had friction slowing down the block. Some people had those two forces working against each other. The main thing was that they worked together. So again, I gave you a point if you just knew, okay, Newton's second law. The next point came from having these two forces work together. And then the final point came from actually having the correct value for our acceleration. What's the direction of the acceleration after the block is cut? It's down the ramp, so that just got you a point. And this one, goodness gracious, the magnitude of the acceleration of the hanging object. Ay, 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 ay. There's no more tension. It's just in free fall. What's its acceleration, G? It's G. So that was just 1 point for knowing that a falling thing accelerates at the rate at which things fall. So part C was worth 5 points altogether. And part D was back to just kinematics. Assume the block was moving up the ramp at 2 meters per second when the string is cut. How far up the ramp is it going to go? So this, you could have used V final squared is V initial squared plus 2A and then delta X. You know that your V final is 0. Oops. Your V initial, if you, and this is where the mistakes were made, if you said up the ramp was positive, then your acceleration needs to be negative, whatever you got for that acceleration. And then you would just solve for that delta x. Doing that, you should have gotten a displacement of, 0.348 meters, or sorry, 0.341. As long as you use, if you used gravity as 10 to get this acceleration. So point breakdown for that, if you had the correct kinematic to use, and then you substituted in your acceleration that you got from part C, and then you got the correct answer. So 3 points altogether. So that is the walkthrough for the hanging mass free response. It was worth 15 points, and you can go to your other test walkthroughs for your specific test, or you can look at all of them if you want to.